function. So this is our reading group that we just concluded reading Raymond Rouillet's book, Cybernetics and the Origin of Information. We're going to do, I think, a bit of an interlude. Might take probably 2-3 sessions to get through this text. So we're reading an article by Georges Canguilhem. The title in English is The Role of Analogies and Models in Biological Discovery. So this text actually appeared in English translation first and then was published in French later. And the translation appeared in an edited volume in 1963. The title of the volume is Scientific Change, Historical Studies in the Intellectual, Social, and Technical Conditions for Scientific Discovery and Technical Invention from Antiquity to the Present. It's kind of like a 18th century page-long title. So just to give a quick sort of introduction to Canguilhem, because I think maybe he's not that well known, I think, in the Anglophone world. So he's a French philosopher of science, particularly of biology, medicine, associated fields. He's generally sort of associated with Gaston Bachelard as part of this sort of school referred to under the term epistemology, which is not exactly the same as the English equivalent, epistemology. It's more sort of historical, analyzing the concepts used in different by different scientists within a certain field, and is often sort of associated with this idea of a kind of epistemic break. So this idea that there's a kind of rupture or break between sort of pre-scientific or ideological approach to a domain like life or health or whatever it is, and then the sort of transformation that occurs in the sort of founding of a scientific approach to that domain. That's a sort of very like compressed and not very adequate sort of expression of this idea of an intellectual break or conceptual break. And so this text I chose it as our sort of interlude between Rouillet readings because, well, for one thing, because the text I had originally suggested is not actually translated is not fully translated. There's a partial English translation, but no complete one. Whereas this one, has a complete translation. And also because there's some discussion of cybernetics within this text, which is, of course, what we were discussing in the Rouillet book. So yeah, it has some connections to what we were reading before, and yeah, so I think it's worth sort of looking at the same questions, but from a very different angle. And yeah, so as the title indicates, it's about models, like what exactly is a model in biology, what kind of thinking is involved in using a model to understand a certain process or organ or function within a living being. And yeah, so he's going to give, well, we'll see as we go along, but he's going to give an explanation of why models are only sort of intellectually fruitful or useful for scientific investigation when they break with a kind of common sense analogy. So there are certain parts of a living being that you can sort of look at and see, oh, this is like a lever, or it has an analogy to some kind of device that human beings build, a technical object, and it's only when we sort of break with that immediate sort of common sense, obvious in scare quotes, perception of the parts of this living being as analogous to a technical object that the model actually gets us anywhere, rather than just sort of importing knowledge that we already have of the operation of this technical object into our understanding of the living being, which may or may not be, a good way of understanding that element of the living being. And yeah, so cybernetics is a different, is an attempt to, form these models using technical apparatus, in particular the electronic equipment that was being developed in the 1950s and so on, using that kind of equipment as a model for the functioning of living beings. And yeah, so Canguilhem is going to sort of investigate to what extent that is an actual model in the fruitful sense, or just an analogy in the sense of like sort of observing a similarity. Okay, so we can, I think, jump into the text. Yeah, for those who haven't participated in this group before, so what we generally do is we read about a page or so of the text and then stop and discuss, ask questions, make comments, etc. Yeah, and then we pick up the next bit. So yeah, the idea is to work through it together, and if there are things that we don't understand or find difficult, or maybe disagree with, then we can discuss that. So maybe, yeah, Angus, would you like to read the first page or so?
Yeah, I can read. This paper is called The Role of Analogies and Models in Biological Discovery. It is not easy to agree on the role and significance of fields in the physical sciences. Boltzmann not has Maxwell's form entirely against fields, but Pierre do the same Maxwell by renouncing the use of any. It seems to be in significant sciences, even to, in fact, since this word refers to corresponding analogous features for all object, and sometimes to a system of semantic and sentence set up concerning relationship and constituent elements of a structure. Without doubt, that in biology have and still used the models. The fact is that explanation reduction is more naive than explanationalized to doubt. It is also the study of which is susceptible of direct first among the relationships involved. But these relationships have no character, and as opposed to pretend to appearance of goodness. The models studied at X make their actions to etiological description. On the other hand, the reduction of structures and functions to forms mechanisms, which are already used in biology realms of physical experience, has had for a long time and still has a breadth of usage directly be no question such, but it seems to me a concept of organs provides of itself, and by the directing principle we understand eminence of it. It has not been sufficiently noticed how full in Western science is for organs, viscera, segments, or regions of the organism expressing messages. Sometimes the name only serves to disguise a comparison, scaffold, for instance. Sometimes the name also indicates an analogous vessel, anastomosis, sac, axis. The Greek and macroscopic, the technical forms, the observation forms. Verse tools are often words of arm. As a result of this fact, consider the explicit use of as the systematic considered extension inherent in Nancy's wounds. Compares the door hinges, yes, vessels to yes. Is not Plato to the summer procedure for explaining physical things. It's Aristotle when he bears the bones of the flexed by the nerves, with the arms of a cow and back bulls. Physiology was, first of all, a discourse de usu partium, apparently, in fact, among its novels, mechanisms suggested were structures, which, so I think in the second, this distinction between two types of models. One, mathematical, which he says concerns the relationship, the elements of a structure. And later on, he'll talk about Fourier's discoveries and be described in the same differential equations. And then the other type of model is a comparison between some natural system, like a tool or a machine of some use that biology is not really susceptible. It's difficult to use them. It's much easier and sometimes necessary to use the artifacts. This can encourage reductionism. I guess now he's just setting the stage. There are interesting points about how anatomical images direct comparison to tools being described as a sack is tool analogy in the essence of axis, or and conversely there are a lot of parts of tools that would describe like the claws of a hammer, for instance. So this is an old comparison, maybe as old as anatomy itself, I think is what Emma is suggesting.
This is older than Simondon's individuation book, right?
Yes, I think so.
Yeah, I think that this sounds like this analysis comparing the tools to like the Simondo. I think like kind of really expands on that sort of critique of Aristotle, I think, and hylomorphism stuff. I think inspired. I don't know. I'd probably like inspired by.
Yeah, it's a great point. That's something on this first pages too. Is Simondon makes a very similar. Hylomorphism itself has a sociotech.
Yeah, I was just trying to look up the dates. So the individuation book, yeah, so it has a kind of strange publication history because it was only part of it was published at first. So 1964 was the partial publication, and then the full text was only published in like I think 2005. But I can't remember what year. So that was one of his theses. Like in France at that time, he had to do two theses. And I can't remember what year he defended that thesis, but it was several years before that. So Canguilhem may have known that text already at the time he was writing this one. So yeah, there may be sort of interaction between these two texts. I'm not 100% sure of that.
I don't know. Maybe this is like going is the critique of putting the analogical sort of like comparing every all these like body parts to like tools and stuff. Is it kind of like is it problematic with like some of the ways evolution is kind of understood, where like the process kind of comes first or whatever? It's kind of the way, or that maybe without getting into like a more technical of like the theory of how like evolution works, because like you're saying like because like you might be snuggling, it's like there's a worry that might be snuggling in some sort of like uh like unwarranted like old school like teleology in some ways. That like a worry at all, or that maybe being critiqued or something, or,
Um,
or
yeah, I think that's related to what's going on here, but I think it's maybe not the primary focus. So yeah, so obviously comparing using a sort of analogical way of understanding the organs of an animal, by sort of grasping this organ as a kind of tool, or as using our experience of tool use and production as a way of understanding the organs of an animal. This is obviously a very teleological way of understanding these organs, that like, the claws are for cutting or grasping or whatever, in the same way that, the similar tool that you build, is made for that purpose. And of course, so that this and this sort of perception of certain parts of animals as being for something, as having a function, is one of the major problems for like an evolutionary account. Is how do you account for this functionality? Like that a wing is obviously in some sense for flying, but if we want to sort of explain the emergence of animals that have wings and can fly without appealing to something like a creator who thinks that making flying animals is good, or a purpose to try to achieve, then yeah, you need to have some sort of alternate explanation for how something like a function can arise out of something other than an intention, in that sense of trying to achieve a certain goal that you're sort of like consciously pursuing. So yeah, it's definitely related, but I think in this text he's not so much interested in evolution, like the concept of evolution, and the place of teleology in the theory of evolution. What he's interested in here, I think, is primarily the relationship between this sort of common sense, or like sort of immediate perception of organs as analogous to tools. What's the relationship between this sort of analogical tool perception and a maybe more conceptual or theoretical model conception, or way of grasping what an organism is, or how an organism functions in terms of models, and what is the difference between a model in that sense and an analogy in the sense of seeing the claw as for cutting or grasping. Yeah, so I see in the chat here, Organelles has a question. So analogy reduces this to an already achieved teleological end and constricts the explanation of function within its analogs already conceived of function. Yeah, I think that's a good way of putting it. So yeah, like when you sort of see the claw as for scratching, then you already sort of know, in scare quotes, you think what the claw is for. You sort of like, this claw is the same as the claw of the hammer that I make, so therefore it does the same thing. And of course, when later physiologists have studied some of these organs that seem to have this immediate function, we find that there are like 5 or 10 other functions that were a lot less immediately obvious. That the same organ is not sort of for one specific thing; it does many things, and many of those functions are not obvious. And then also, of course, there are many organs in an animal that don't have this sort of immediately perceptible function, and you can only determine what function these organs have by doing experiments and developing a theory of what the organ is doing. So yeah, the sort of analogical perception, it kind of short circuits the theoretical investigation of what the theoretical and experimental investigation of what this organ is doing, by just sort of having this immediate perception of what you think it's doing, based on like a sort of overall comparison with a tool that has like a similar shape or something like that.
Or questions that people want to keep.
Yeah, we can go on to the next bit. So if someone else could read from the line "one must admit" and read about a page from there. Sure. Yeah. Thanks.
Okay. One must admit to the bottom of page 3, I guess, something like that.
Yeah, I think that works. Yeah, at the end, there's a quote at the end of the page. You can read to the end of that quote.
Okay. One must admit that the use of mechanical models in zoology and in the study of the peculiar animal functions of locomotion is first justified by the fact that in vertebrates the organs of local movement are articulated. If one understands by articulated a kind of mechanism of which the constituent parts are moved, while two of their extremities always remain in contact, it must be admitted that articulation is practically the only type of mechanism presented by living organisms. The explanation of the peculiar features of locomotion has thus been able to proceed by the establishment of analogies with human techniques, taken as models in the wide sense of this term. It is thus that Borelli, then Camper, explains the swimming action of the fish by comparing the movements of the caudal fin with those of an oar used as a rudder. The criticisms put forward by Barthez of this explanation constitute a model of the objections, vitalist in inspiration, which are periodically raised against the use of reductive models in biology. Criticism, which have Criticisms which have not prevented the resuscitation, like bringing resuscitation and use of Mary, and by R.J. Gray most recently of the Borelli-Camper model. This crude use of the technical model in biology is so spontaneous and so implicit that it has been possible, as I have noted before, to misunderstand for a long time its presence in the methodology of anatomical deduction. Cornell, writing in 1868, drew attention to the fact that Harvey had noticed so clearly an analogy between the valves of veins and mechanical valves. In fact, Harvey said, lock gates, that he had been irresistibly led to induce the law of circulation. In this case, added Cornell, the organ is so precisely appropriate to its function that one is able to pass without hesitation from the organ to its function. Yet a dozen years previously, Claude Bernard had cleverly refuted the false simplicity of this methodological outline to the mistaken history of the embodiment of a function in a structure. He opposed the impossibility of deducing from an anatomical examination knowledge of a functional nature other than that which had been introduced into it. It was already known by common experience what it was meant by a reservoir, a canal, a lever, or a hinge. When, as simple comparison, it was said that the bladder must be a reservoir for the purpose of containing liquids, that the arteries and the veins were canals destined to conduct fluids, and the bones and joints played the parts of scaffoldings, hinges, levers, etc.
Right. So this is sort of giving some some examples of this analogical perception of organs, and maybe he points to like maybe the most basic of these analogical perceptions in the limbs of vertebrates. So legs, arms, etc. And so these are very clearly they clearly operate on similar principles to a lever that we might use as a technical device to lift something. So you have a hinge, you have a joint in that connects the leg to the torso, for example, and then you're sort of levering the body of the organism forward by moving one end of the leg. And so this is maybe like the most immediately visible kind of technical analogy in understanding the functions of organs. And then you can make similar kinds of analogical analogies in the case of fish, for example, how this example of the caudal fin. So this is the fin at the back of a fish. So as it's swimming, it can sort of use this fin to change direction in the same way that when you're in a boat, for example, you can stick the oar backward, at the back of the boat, and use it, by turning it to the left or right. You can turn the boat in the opposite direction. And then Canguilhem here mentions this sort of criticism of this sort of analogical approach in terms of this sort of vitalist rejection of reductionism. So it's sort of saying that, this comparison of the fin to the oar is too simplistic. It doesn't account for like the complexity of the functioning of the fish, etc. And so there's a kind of a recurring criticism of this kind of analogical technical model approach. But at the same time, the same kind of technical analogy just keeps recurring. So it's kind of a recurring, debate between either, comparing these organs to technical apparatus on the one hand, and then saying, no, that's too simplistic on the other hand. And you have this sort of repeated, resurrection of this back and forth over and over again over the centuries. And then he points to another, maybe a more sophisticated example of this technical analogy in the case of the circulatory system. So Harvey in the 17th century was, I think, the first person who had identified that the blood is actually circulating through the body. So it leaves the heart, passes through the blood vessels to the different organs and so on, and then it comes back from those organs to the heart. It's a sort of closed system. And what Harvey had pointed out is that there are these sort of elements within the veins that prevent the blood from moving in the wrong direction. So moving counter to the circulation from the heart to the organs and back to the heart. So the blood can only move in one way if everything is operating as normal. And so Harvey had compared this to the translation is not super clear here, but in French it's clear that this is talking about systems of canals where there is a lock where you essentially to level to allow a ship to pass from a lower level to a higher level. So you open up the lock, it fills up with water, and the water level rises. The boat can pass, or the ship or whatever can pass to the next step. It's kind of like a set of stairs to go from a lower body of water to a higher one. So that's what Harvey had used as his analogy for these structures within the circulatory system. So they ensure that the water, or in this case the blood, flows in one direction and not the other, and it can't flow in the other direction. And then so he quotes this passage from Cournot where he is commenting on Harvey's discovery, and he makes this exact sort of claim that you can like directly see the function of these structures just by looking at them. So you immediately see this organ is exactly like a lock in a canal or a valve in a pump system or something like that. You just immediately see this analogy, and then you know what the function of this organ is. But then Canguilhem points out that this sort of immediately seeing the function of something had already been criticized 12 years earlier by Claude Bernard, who was one of the sort of leading figures of 19th century French physiology. He is, I think, if I remember correctly, he was the one who first identified the role of insulin in diabetes, which obviously is a huge discovery for medicine. But yeah, so he insists on the need for experiment to understand the function of some organ. Like you can't just look at an organ and say, oh, it does this. You have to, in his case, a lot of these experiments involved destroying the organ and seeing what happens to the animal. It's obviously a pretty brutal experiment for the animals, but yeah, that was how he conducted these experiments. And then, so he points out in this passage that when you sort of import these descriptions of technical apparatus as your way of understanding the organ, you aren't really gaining any theoretical knowledge that wasn't already in that concept. So when you say the bladder is a reservoir for holding liquid, you have a certain understanding of what reservoirs do, how they hold liquid, etc. But then you just sort of bring that knowledge in and apply it to the bladder. But then you're sort of dependent on these pre-existing stock of descriptions of technical apparatus, and you're not really producing new knowledge. You're just sort of applying existing concepts to certain. I mean, it might be useful to understand the reservoir nature of the bladder, for example, but you aren't really gaining any new knowledge. Whereas when you conduct physiological experiments and discover the role of insulin in regulating blood sugar and so on, then you're actually creating a new sort of theoretical knowledge of the functioning of this important system in within the animal, physiology. So yeah, it's this very sort of direct. It's a sort of contrast between this very direct analogical importing of existing concepts versus creating new theoretical knowledge through experiment.
Thinking of like, I don't know, just a stupid thing of like, oh, we use like an analogy to like, of like, to like describe, oh, like the fish is like the the fins are like the oars, but then what if it's like a fish? It's like this mud skippers where they go out of like the land, and we say the fish their their fins are like, now it's like a different analogy. We're like analogizing the analogy, and we just layer them on top of each other because and never get to like, I don't know. It's just a silly thing I thought of. Like we grounded it in like an analogy in the first place or whatever, and then we just keep layering them on top of each other whenever we meet a counterexample of something.
Yeah, so it's an interesting sort of problem for this analogical sort of technical, the technical analogies that, yeah, as you pointed out, like an organ, might have one function in a certain environment or a certain context, but it's often the case that the animal is not sort of bound to one specific context, even if that's sort of its preferred habitat. Sometimes you have these fish that can crawl across land to, from one body. From what, yeah, the fins are like oars if the oars were being used as legs. Yeah, exactly. So you have the organ is sort of used for one function in a certain context, but then that animal can sometimes move into a different context and use those organs in a different way. And so, and then sort of the reverse of this is that, of course, like many land animals, like say a dog, for example, can swim if they're in the water, so they're using their legs to paddle, which obviously is not the sort of primary function of a dog's legs, but it's something that the dog can do. So if you sort of if your only understanding of a leg is that it's a lever, then you have to come up with like a new analogy to explain how the dog uses its legs to paddle when it's in the water. Or conversely, yeah, if you only understand the fish's fins as oars, then you have to come up with like a new analogy when the fish starts crawling across the mud to reach another body of water. So it's again, because it's such a sort of like immediate, like pinning this analogy onto this one organ. It's sort of very bound to that one specific context in which you're seeing this organ, and then in some new context where that organ is being used in a different way, you have to sort of start from zero again. You have to find a new analogy, and then like what relationship is there between the oar fin and the lever fin? Like you have these sort of two different analogies, and it's not clear what connection they would have to each other, etc. So yeah, it's again because you have this sort of very immediate connection between the concept or the image that you're using to understand this organ, and then the function of that organ within the context in which you're examining it. And then because there's no gap between them, it becomes so bound to that context that you have to sort of make a new label when you move to a different context. So there's a comment here from Organelles again in the chat, so saying that there's so this sort of approach implies that there's like a singular function of an organ that you just have to discover, that it's already there, you just sort of see it and then you discovered it. So it makes it harder to sort of fit that function into an understanding of the organism as a whole and how it functions, in relation to the other organs of that organism. Yeah, so I think that's exactly right. And so this is because this analogical perception of the organism is dedicated to understanding parts of the organism. So like the leg is a lever, the fin is an oar, etc. It sort of, and this is sort of the vitalist criticism that is made, that is a kind of reductionism, because you're sort of taking this organism, you're like dissecting it into these parts, and you look at each of the parts and say, what kind of technical device does this remind me of? But then, of course, a fish is not just like a collection of levers and oars and so on that are like sort of randomly assembled. Even if the different parts of a fish have functions that in some cases can be compared to the functions of different technical devices. Obviously, a fish is not simply a bunch of technical devices that are assembled in various ways. It's an organism that, for one thing, it produces itself out of an embryo. So all these different the fins and gills and all the different organs that make up a fish are produced by the fish itself in the course of its development. And then when it's an adult fish, it also keeps itself in existence by taking in nutrients and reproducing its organs, etc. So it's very different than the way that any human produced technical device operates. And then even so that, this is sort of what I was getting at earlier, that when you so another comment from organelles in the chat here. So when you sort of have this immediate sort of analogy between the fin and an oar, and then another immediate analogy between the fin and a lever in a different context, these are basically just different organs in the sense that they're sort of because you're sort of grasping the organ through this analogy with a technical device. When you have to use a different technical analogy, you are essentially grasping the organ as a different organ, and so you can't sort of identify the organ that is being used in these two different ways. You're grasping like two different organs, even if they sort of coincide in the actual fish.
No, fishes are just a bunch of walkie-talkies taped together.
Yeah, exactly. Yeah, that's sort of like the parody version of the reductionist approach to physiology. Is you just go to a Radio Shack and buy a bunch of little mechanical parts or whatever, and you put them together in the right way, and that's the fish. You've developed a model for a living organism. Of course, when I say that's a parody, because of course no one even the most sort of extreme reductionists in biology would never sort of put it in those terms. But so this is, and maybe I could have mentioned this at the beginning, that Canguilhem is sometimes described as a kind of rationalist vitalist or vitalist rationalist. So he's very interested in these sort of reductionist or mechanicist biologists, that he obviously recognizes that there's been really important and insightful work done by sort of understanding the mechanisms involved in physiological processes and dissecting organisms and finding out how the different parts work and so on. But he also insists on I'm sort of trying to explain this a little bit now, what exactly vitalist means here. So he also insists on the fact that when you do that kind of breaking down of an organism into parts and understand how the different parts work and interact with each other, that doesn't sort of eliminate the organism as a living being as such. So even if you understand how the parts all operate and how they interact with each other, there's still this kind of intellectual insistence on the fact that the organism as a living being, or maybe better point would be just to say the living being is not reducible to the parts, in the sense that there's a kind of insistence on the need to grasp the living being as such, as an entity that solves problems in its interactions with its environment, for example, as opposed to like a collection of parts that have been produced somehow and that are connected to each other in various ways. And so this is one of his other books. Probably his most famous book is The Normal and the Pathological. And so he's building in that book, he's building on the work of Kurt Goldstein, a neurologist who had studied people who had suffered neurological damage in World War One. And so what Goldstein insists on in that book, or one of the main things he insists on in that book, is that these, people who have suffered brain injuries or neurological injuries are not just it's not just that they've sort of lost a certain function, that you can take the normal person and subtract the one function that has been damaged. Yeah, or French Schneider. Yeah, so this is one of the case studies from Goldstein. So you can't just say, okay, this person no longer has the capacity to recognize certain shapes or whatever. It's this person has suffered this injury and has lost certain capacities, but they are adapting, their remaining capacities to try to perform the different tasks that they have to do to go through their lives. So someone who can't recognize faces anymore because of an injury, for example, they might I don't know, maybe pay more attention to the clothes that people wear and try to recognize the person based on what clothes they wear. This is a sort of simplistic analogy, but like, yeah. So in any case where there's like a loss of a certain function, due to injury or whatever, it's not just like sort of subtracting this one operation of a certain component of a machine. It's by the organism as a whole, the living being that is dealing with this environment and trying to keep itself in existence and pursue its goals, etc. This organism adapts to the inability to perform certain functions that it could perform earlier by taking detours in various ways or doing things in a different way than it would previously. And so this is sort of characteristic of living beings as a whole, that they're this sort of problem-solving activity that, of course, operates by means of mechanisms of various kinds. We have like the circulatory system that pumps blood, etc. But the sort of problem-solving capacity is more fundamental than the mechanisms by means of which some of those problems are solved.
Something contingency in nature. I don't know, something like that, right?
Yeah, I mean, this does have connections with questions about contingency and necessity. And so, like, for example, in the case of living organisms, mechanism or reductionism is often connected to ideas of determinism. And so, like, for example, genetic determinism. So this is sort of like a position that would argue that the genetic pattern involved in the development of the organism kind of determines what the organism does over the course of its life. And so, yeah, this is a kind of reductionism in the sense that it sort of reduces the whole developmental process to the pattern of genes. And then it's also a determinism in the sense that, once that genetic pattern is set, the sort of life course of that organism is already set as well. And yeah, so the sort of the rationalist vitalism kind of response to that position would again be just sort of insisting on the fact that the genetic pattern is like in itself inert. It's just a sequence of nucleic acids. And so it's only because that genetic pattern is used by the cell to produce proteins, and those proteins are involved in all sorts of physiological processes, et cetera, et cetera. So it's only because that genetic pattern is part of this problem-solving activity of the organism as a whole that it has any actual like physiological function or activity. Outside of an organism, a strand of DNA is just a sequence of nucleic acids that doesn't do anything, and so it's only in conjunction with or in connection with that problem-solving activity that this genetic pattern actually does anything. And so, yeah, that's sort of like the vitalist rationalist or rationalist vitalist response to that kind of determinism. So in that sense, it sort of it's anti-deterministic in the sense that it sees the organism as responding in these flexible ways to its environment, rather than being sort of programmed. The sort of Dawkins idea of the genes as sort of controlling the organism.
Keep reading on. Did you say do you get a call or something in the hour, or do you think 2 hours by now?
Right. Yeah, I haven't gotten that email, so it looks like my other thing is not happening. So we'll continue for the another 45 minutes or an hour or so. So we can go on to the next passage. If someone else could read from the top of page 510, or the fourth page of the PDF. So beginning with at the time.
Like, I need to give me a second. I just gotta get off of the Android app. It's glitching on me, so just give me 1 second. All right, can y'all hear me?
Yes. Yeah.
Okay, so at the time, the term model had not yet gained a place in the normal vocabulary of epistemology, but the formula by which Bernard summed up the samples can be accepted as an early definition of the term. Quote, analogous forms were brought together and similar functions were inferred. It would evidently be an exaggeration to attribute great heuristic efficient use of a summary technological model. To return to the discovery of the circulation, Harvey seizing upon the anti-retrograde function of the valves of the vein only constitutes one of the arguments for his thesis, the confirmation of his third supposition. The systematic use in the 17th and 18th centuries of references to mechanisms analogous to organs, inspired by Galilean in a new image of the world, cannot be credited with decisive discoveries in biology, even if it did not remain merely a philosophical or literary. It is worth noting that recent apologists for heuristic efficiency in biology, especially in neurology, of cybernetic mechanisms and of feedback models, consider the construction of classical automata, that is to say, those lacking some sort of feedback mechanism, capable of simulating, within the limits of one or more rigid program, animal behavior or human gestures, to be just a craze, without any scientific interest, merely a pastime. And yet, in a very original study of the history of biomechanism, A. Doyon and L. Liagra have revealed the connection in the 18th century between medical research and the construction of mechanical apparatus, quote, moving anatomies or, quote, automatic figures, according to the terms used by Valken. The quoted text taken from Quesnay, Valkenson, and Lequet do not indeed leave any doubt that their common plan was to use the resources of automatism as a dodge, or as a trick with theoretical intent, in order to elucidate the mechanism of physiological functions by the reduction of the unknown to the known, and by complete reproduction of analogous effects in an experimentally intelligible. The Cartesian animal machine remained a manifesto, a philosophical war machine. It did not constitute the program, scheme, or plan of construction of any particular description of function or structure. On the contrary, the attention given by Valkenson and Lequet to the elaboration of detailed plans with a construction of simulators, and the spectacular public success of the efforts of the first of these biomechanics, must allow us to carry back to the 18th century at least the explicit recognition of a heuristic method, using under the name of imitation recourse to analogical models of function. Condorcet, in his Éloge des Valkens, grasped perfectly the difference between a simulation of effect sought as a sort of game or means of mystification, and a reproduction of means of action. Today one says a construction of pattern, with the aim of obtaining experimental evidence of a biological mechanism. Speaking of Valkenson's first automaton, the flautist, Condorcet writes, quote, some of these men who believe themselves to be wise because they are suspicious and credulous saw in the flautist only a bird organ, and considered as quackery the movements of the fingers, which imitated those of a man. Eventually, the Academy of Science was charged with examining the automaton, and decided that the mechanism used to give forth the sounds of the flute rigorously executed the same operation as someone playing a flute, and that the mechanic had imitated at once the effects and the methods of nature within an exactitude and perfection that even people most accustomed to prodigies of art would not have imagined to be attainable.
Yeah, so this is talks about this interesting moment in 17th century technology, I guess you could say. So there was this guy, Vaucanson, who Descartes mentions, I think, at least once. He was he was famous for developing these sort of hydraulic machines, I guess you could call them, that were set up around Versailles. So it like used water pumps to kind of animate these figures. Descartes talks about one where, like, if you step on a certain like tile in the garden or whatever, it makes the figures move and they sort of run or something. I can't remember exactly what it does, but anyway, so these were partly, they were just sort of like a party trick. It was kind of like this amusing apparatus for the court, elites to be impressed by. But then so Canguilhem here points out that the cyberneticians often sort of look down on this type of machine as precisely just this kind of party trick, and not really telling us anything about how the sort of animal bodies that are being simulated by these machines actually operate. And precisely, for the cyberneticians, it's precisely because these machines have no feedback mechanism. So the running figure, for example, doesn't sort of react to the surface that is running on and change the way it runs to adapt to it in the way that a human or any other animal that is running changes its gait based on what kind of surface it's running on. So like these machines have a sort of preset program. It's triggered by stepping on this tile, and then it just sort of runs in a linear way. It doesn't have any response to the way that it's running, and then sort of modify its functioning to adapt to that to the way it's running. And so this is sort of the argument among the cyberneticians for why these machines are not really useful or like a good model for how living organisms and animals in particular function. But Canguilhem points to these studies that have been done, obviously much later in the 20th century of Vaucanson's work, and some of the commentary that was done at the time, investigating some of his machines, and suggests that there actually was much more like I guess physiological realism in these machines than maybe was earlier understood. So this flute playing machine, the movements of the hands that sort of play the flute are actually quite similar to the movements of the hands of a real flute player. Although obviously the sort of underlying mechanism is quite different, and there's no muscles in this hydraulic machine. It's operated by water or air or whatever it is. But the movements that are produced are similar, even if the way the movements are produced is different. And so it's not completely just a sort of game or party trick or whatever. It's simulating the effect of playing the flute, but it's also doing so in a way that grasps some of the mechanisms that are involved in human playing the flute. So it's not completely alien to, I guess, a real physiological study of how a human moves their hands. And these hydraulic machines were very important as a sort of inspiration for Descartes. Like his whole physiology is based on hydrodynamics, essentially. That he conceives the nerves as being tiny sort of hydraulic actuators, essentially. That so the muscles, for example, are pumped full of the animal spirits that flow through the nerves, and that makes them, expand or contract in ways that move the limbs, etc. So yeah, this is like Descartes' whole model for how the body operates is basically drawn from these hydraulic machines.
I was saying, like, it's interesting that the accurate, like, use of, like, the hand or whatever is one where it's using a tool, where, like, a recurring theme of this analysis when, like, body parts are analogized to tools. And it seems like that these machines are good at, like, replicating the hand when it's, like, up, when it's engaging with a tool-like thing, like an instrument.
Yeah, so in this case, the flute player, for example, there's a very limited sort of stereotype set of movements that you either press down on a certain hole or you lift the finger off a certain hole, and so it's relatively straightforward to model to simulate the movements of the fingers, either pressing down or lifting up. And yeah, so exactly as Angus points out in the chat here, if you were to take this flute player and put a guitar in its hands, it would probably just mangle the instrument or I don't know exactly what would happen, but it would be a disaster in any case. Whereas of course a human, even a flute player who has never played guitar before, doesn't know how to play guitar, would at least sort of know how to adapt their grip to a different instrument, and they would at least understand that they can't use the same movements that they would in playing the flute to play the guitar, like the very minimal sort of recognition that this is a different object and my hands have to move in a different way. And so this is something that, of course, so this is sort of the cybernetic objection, again, in the sense that the flute playing hydraulic machine has no sort of response to what is actually in its hands. It's just the hands are sort of preset to move in a certain way that reproduces the movements of the flute player, but it's not actually sort of grasping the fact that there is a flute in its hands. Like if you just sort of took the flute playing device and removed the flute from its hands and you took it out of the hands, it would keep doing the same movements with its fingers, even though there's no sound coming out. So yeah, again, this is just sort of like a very simplistic machine in the sense that it's not actually responding to its environment in any way. It's just sort of doing this preset pattern, and it's precisely when human movements are following this kind of preset pattern in this way that it's most straightforward to simulate them in a machine. And then the much more difficult kinds of human movements are the ones that do involve some sort of response to the environment in a flexible way, and especially an environment that is changing, and something like I'm thinking of, I don't know, say like massage or something like that. You have these, of course, like mechanical roller type massage things, but like a human performing a massage is responding to the tension of the muscles of the person, and whether they seem to be expressing discomfort or pain or etc. And so this flexible adaptation to this like soft moving body and the what the person is saying and so on. This is something that is much harder to simulate, of course, than the up and down movements of the fingers that the flute player is performing.
No hesitation.
Yeah,
Sorry, oh, sorry, go ahead.
oh, I can wait. Sorry, if you were talking, I can come back.
Oh, I was just going to ask what you mean by no hesitation.
When you when you react to something, you can like kind of hesitate. That you can pull back a bit, but like you're just like pushing. You're just in inertia. You're like a machine, or less like a wall, like something rolling down a hill.
Yeah, so I think like maybe you can think of like even sticking with the realm of music, for example, like when you're sort of learning an instrument, you'll practice scales and arpeggios and so on, and you're sort of you're almost like this sort of connects with some of the things that we discussed when we were reading Rouillet. You're sort of like building a kind of mechanical pattern within yourself. You're like a kind of psychological machine in the sense that you sort of make yourself capable of running through a scale without having to think about, okay, what's the next note, et cetera, et cetera. You just sort of run through this pattern without even thinking about it. And then of course the goal is not just to be able to mechanically run through scales, which is not a particularly musically interesting pattern to perform, but then by sort of making yourself capable of running through these patterns without thinking, you are hopefully making yourself able to play more interesting patterns, actual musical compositions, without having to sort of stop and think, okay, now I have to move my finger here, like this is the next note is as in this place, etc. You just sort of like without even thinking, you sort of immediately get to where the next note is, and so yeah, you sort of produce this mechanical or this psychological habit, the psychological mechanism through habit, but you do so with the purpose of allowing yourself to perform this much more interesting, creative, expressive pattern in the form of a musical composition, sort of without having to stop and sort of think about where your finger has to go next at each moment.
Something organelles.
Yeah, and I may be way off here, but I'm also in this passage. And maybe this is what everyone's saying, and I'm just completely missing the point. But it also seems like he's sort of he's pointing out the big flaw in this in all of this, and that in this type of explanation there's the illusion of understanding, and that it's really just kind of self-deception that's taking place here with our scientific understanding of these things. There's some of the language he uses here. He says under well, let me just read this quote that he has. A couple of the language, he's kind of mocking them here, who believe themselves to be wise. And then he says, eventually, the Academy of Science, charged with examining the automaton, decided that the mechanism used to give forth the sounds of the flute rigorously executed the same operations. Basically, he's pointing out that they're just relying on analogy as their method of explanation without an actual understanding. Is that kind of what he's getting at? That by using analogy, we can just now say, well, this is what it means. We can apply meaning however we want to.
Yeah, so I think this discussion of the Vaucanson devices is a little bit of a different. So it's not exactly the same point as he was making earlier when he's talking about this sort of immediate analogical perception of the organs as having the same function as a similarly shaped technical apparatus. So here he's sort of, I guess, going through this transition, or he's walking us through this transition between this sort of immediate technical analogy on the one hand and something like a model in the modern sense on the other hand. So these Vaucanson machines are sort of maybe halfway between the two. So what the question when you're faced with one of these machines, this flute playing machine, for example, is like, is this machine just sort of producing the same effect as the human who plays the flute. It just sort of has the same superficial result, even if the operations are completely different. That would be one possibility. And then the other possibility is that you're not only simulating the effect, but also partly, or to some extent at least, the means of producing that effect. And that, of course, is much more informative when it comes to physiology. That the fact that a bird flies, for example, that the wings are involved in flying. If you can simulate flying of a bird by building an airplane that also has wings, obviously this doesn't tell you a lot about how the wings of a bird function, because the airplane is producing this flying effect in a completely different way than the bird is. But if you produced like a robot that flew by flapping its wings and had something like feathers and so on, that was like producing the flying effect in a similar way that the bird produces the flying effect, then you might actually learn something about how a bird flies by producing this machine and seeing how the different parts have to be connected to each other, how heavy the machine can be with a certain wingspan, et cetera, et cetera. So the question, or what Kondo says, is arguing in his discussion here of the Vaucanson machines, is that they are not only producing like the superficial flute playing effect that is like sort of an entertainment value only. It doesn't really tell us anything about physiology, but they're also sort of reproducing the movements of the hands in the human flute player in a way that does actually tell us something about the human flute player's performance. So even if the sort of more fine-grained mechanisms of how the hands are moved is quite different, it still gives us some better understanding of those movements by trying to build a device that performs the same movements. Yeah, so it's still a limited, of course, understanding, but it's getting us closer to a theoretical grasp of the human flute player's performance, rather than just sort of simulating in a very superficial sense.
Yeah, I think what Angus wrote here with this being wary of the ontological overreach of doing this. And so I guess what I'm seeing in this little passage is he's pointing out that there's still sort of a sleight of hand trick here that we play when we change this method. So it may be more effective, but we still need to be careful, because we're kind of forcing it in a way still. But
yeah, so he's going to go on. Well, we'll see this in the next section that we read, but he's going to go on to talk about the sort of major limitation that we've been discussing of these Vaucanson machines is precisely the fact that they don't have any feedback mechanism. They don't sort of take in any information about even the what is the result of moving the fingers in a certain way. Like, is there any sound actually being produced or not? That is not even integrated into the functioning of this machine at all. It just runs through a preset pattern of finger movements using the hydraulic mechanism. And so the cyberneticians think that if you just sort of add in this feedback mechanism, that, like, say you have a microphone that sort of listens to the sound output and feeds it back into this hydraulic mechanism, and then like modifies the way the fingers move based on whether the sound is correct or not. Like, yeah, you could think of like a way of doing this that would sort of introduce this feedback system. And then the cyberneticians think that this is sort of like solving the problem that you've like, the Vaucanson machines are not good models of biological organisms because they don't have this feedback function. And then if you just add in the feedback, then you've gotten a good model of a living organism through this cybernetic feedback sort of operation. And of course, yeah, Canguilhem is he says, yes, these are better machines, these are better models of living organisms, but still you're still sort of missing the point. Just by making a more sophisticated machine, you haven't like sort of entirely grasped a living organism as this, as I was saying, this sort of like problem solving, inventive activity. You've gotten a better model that allows you to learn more about living organisms, but you haven't sort of you can't reduce the living organism just to a machine with feedback any more than you can like a Vaucanson type hydraulic machine without feedback.
Yeah, thank you. That makes sense.
Yeah. Thanks for the question. Yeah, it's good to even if you feel like you don't understand something, or you're not clear, or you think my explanation is not good. I'm happy to go over those points as well, because we're working through this together. Okay, so I'll go on to the next one. I can read this passage. Okay. One will doubtless not deny Condorcet a sort of intuition of the ulterior possibilities of construction, or even only of theoretical conception, in the field of mechanisms acting on information as distinct from those simply using energy. He affirms, indeed, that the genius of a mechanic, quote, consists principally in imagining and disposing in space different mechanisms which must produce a given effect and which serve to regulate, distribute, and direct the motive force, unquote. And he adds, quote, one must not look upon the mechanic as an artist who owes his talents or his success to practice. One can invent mechanical works of art without having made or worked a single machine, just as one can find methods of calculating the movements of a star that one has never seen. Sorry, that was an unquote there. Right. This enunciation of a possible evolution of models towards mathematical theory is the theme of a story which we must go over rapidly. For almost 20 years, it has gradually become more and more commonplace to claim that the invention of Watt's governor provided physiologists with the initial model, albeit a non-premeditated one, of a feedback circuit between an effector organ and a receptor one. In fact, for there to be noticed in Watt's arrangement an analogy with a reflex circuit, it was necessary for the methodical exploration of the properties of the nervous system to be made possible by progress in electricity, starting from the observations and experiments of Galvani. It is not from the steam engine, but from the battery and induction coil that were born, by means of technical epigenesis, the electronic assemblies recently promoted to the dignity of feedback models of the functions of the nerves and nervous centers. The first stages of positive neurology are a kind of counterpart to the discovery of the circulation of the blood. Galvani's discovery and Volta's invention established the analogy of the nerve with a conductor of current. Even Galvani's error concerning the existence of animal electricity is explained by the analogical necessity of finding a source of current in the organism. The Bell-Magendie law and the distinction of the functions of the spinal nerve assigned to the propagation of intranervous current a centripetal and a centrifugal direction. The concept of reflex action, Marshall Hall, 1832, J. Müller, 1833, and the schema of the reflex art, E. Wagner, 1844, furnished the elements of a functional system, no longer merely a morphological one. Whilst electricity was becoming, with Ampere and Faraday, a science of dynamic fields and currents, the experiments and polemics of the physiologists, Dubois-Reymond versus Matteucci, were leading to the renunciation of the concept of the passive nerve conducting the impulse, and to the presentation of evidence that its activity is accompanied by the production of electricity. In these conditions, recourse to electrical models in neurology became a familiar practice. And by means of this example, we can understand the reasons why research tends to make use of models. On the one hand, nervous fluid is hypothetical, not something observed like the blood. Thus, a model is necessary as a representational substitute. On the other hand, electric current was first used for the transmission of messages, not of energy, and the priority of this application contributed more than a little to the popularity of the electrical model in neurology. Finally, before the establishment and consolidation of the cellular theory, neurophysiology could not be a physiology of constituent parts, but could only consider the totality of an arrangement. Accordingly, we must make use of a model for the investigation of a phenomenon whose complexity cannot be broken down. Okay, so there's a lot of references in here that not everyone will necessarily be familiar with, so I'm going to try to explain as many of them as I can. So let's see. Oh yeah, so maybe just to start, he describes how Condorcet's sort of defense of the Vaucanson machine sort of is maybe pointing towards the role of information in these machines that is going to obviously become much more important in the next 150 or so years after he's writing, and then in the case of cybernetics, it information is taken as sort of like the central element of what it is that machines and living beings have in common. And this is part of this complicated story of how the information starts to ends up becoming like sort of this central concept in physiology. And so he's just sort of like sketching some of the moments of this story in this passage. So he points to Watt's governor. So this was something that cyberneticians sort of like retroactively sort of took to be like one of the first cybernetic machines or technical devices that operate on cybernetic principles. So this was a device that was invented by James Watt on one of his steam engines that regulated the the power output by the steam engine. So it has, so the steam engine has a kind of rotating cylinder that as the engine operates the cylinder. So it's a vertical cylinder that rotates in a horizontal plane, if you can picture that. And then so as the steam engine is speeding up, the rotation of the cylinder speeds up as well. And then to regulate the power output of the steam engine, he uses these arms that are attached to this cylinder. So there's a hinge at the attachment point of the arm to the cylinder, and then as the cylinder speeds up, the arms are sort of lifted by the rotation, and the lifting of the arms allows more steam to escape from the cylinder, which then causes the machine to slow down. So essentially, the faster the steam engine is running, the more steam escapes, which causes the machine to slow down. And then as the machine slows down, less steam escapes, and it speeds up. So it's sort of, the functioning of the machine has this kind of feedback. There's negative feedback in the sense that the acceleration of the machine causes this feedback, which makes it slow down again. And what this does is that it regulates the output of the steam engine based on how much work is being done by the engine. So if the engine is just sort of running with nothing attached to it, it will just the steam engine will operate at a low output of power. But then if you attach some sort of machine that does work to the steam engine, and so the steam engine has to drive this machine, then it will output more power while still running at the same speed. If that makes sense. So in the earlier models, you had to have in typical sort of 19th century dark satanic mill fashion, they had like a 6-year-old boy that would run, that would operate the machine to the steam engine to ensure that it didn't overheat or go too slowly to run the machines. But now you can replace the 6-year-old boy with this governor that does the same job and doesn't need a salary. So that's the Watt governor. So this is sort of taken to be like the model for like a cybernetic system, sort of the first instance of a cybernetic system. And the word cybernetics itself is etymologically related to the word governor. The cyber bit is it has the Kubernetes is a steersman, and so governor and steersman are sort of related terms. Right, and then so he talks about Watt's governor, and then he talks about Galvani and Volta. So these are two Italian physiologists who investigated the role of electricity, or what we would today describe as electricity, in the nervous system of animals. Galvani had done these experiments with setting up an electrical circuit involving the muscles of a dead frog, which causes the muscles to contract. And this was something, and this was like early 19th century or late 18th century. This is something that was, of course, very sort of surprising and remarkable at the time, that like you seem to be sort of simulating life in this dead frog leg by through this electric circuit, and of course the whole Frankenstein imagery of the lightning bolt that brings the monster back to life. So this is like drawn from this sort of domain of research at the time. So the Bell-Majonzi law, this is something that you find even today in like intro neuroscience textbooks or whatever. So this has to do with the fact that there are two separate fibers of nerves that enter and leave the spinal column. So you have one sort of bundle of nerves that is the efferent nerves. So these are the nerves that carry signals from the brain down the spine into the rest of the body. So the limbs, the heart, the digestive organs, etc. And then you have the opposite direction, the ones that carry signals from the sense organs, the muscles, all this, into the spine and up to the brain. So you have these sort of two different directions, and there are two separate bundles of nerves or fibers that one of them has the afferent sort of nerves, and the other has the efferent nerves, and so they're separate from each other. and then you have this concept of reflex action. So Canguilhem had actually written a whole book on the history of the concept of the reflex action. So this is like the sort of textbook example of this is when you go to the doctor's office and they take the little hammer and hit your kneecap, and then your leg kicks out. And this is something that, so even if you like are sort of aware that this is going to happen and you try to stop yourself, it actually is quite difficult to stop. It's like something that is not really under voluntary control. And so the idea here is that there's this kind of arc where the sensory input of the pressure or the impact on a certain point of your knee is like directly linked to the muscles that produce this kicking action. So there's like a kind of circuit that goes from the input on the knee to the muscles in the leg that causes this kicking action. Okay, next references here, Ampère and Faraday. So these are two of the like leading figures in the development of electromagnetism as a field in physics in the 19th century. And yeah, so they're involved in so electricity was it's a whole complicated subject in its own right. But they were some of the first ones to start looking at electricity as involving currents and fields rather than like these very specific forms of apparatus like a Leyden jar or a voltaic pile, which are the kinds of things that were studied before them. Anyway, so I won't go into too much detail about that, but yeah, more sort of like systematic and maybe abstract conceptions of electricity as this kind of fundamental force of nature rather than this kind of curiosity that certain devices produce. Let's see, what else do we have? Oh yeah. Then maybe this last bit, I think maybe the last one maybe a couple things to describe here. So yeah, the reference here to electric current being used for transmission of messages. This is of course talking about the telegraph, which is like I think mid 19th century is first developed. So of course today we're familiar with all sorts of machinery that operates on electricity, that you have like a generator or a power plant that feeds electricity to a machine, and the machine has an electric motor. But that was not the case in the until the late 19th century. Like throughout the 19th century, the main use of electricity in like sort of practical life was for transmitting messages through the telegraph. And so so you have like, on the one hand, you have these experiments with the frog legs that I was describing, that you see there's clearly some sort of role of electricity or connection between electricity and movements of animals. And then on the other hand, the sort of familiar technical application of electricity in the 19th century is also transmitting information or messages. And so it's not hard to see why it starts to become very appealing to consider that like the nervous system, which functions using electricity in some not really clearly understood way, must be transmitting messages. So that's sort of where that connection comes from. And then I think the last point to explain here is the bit about cellular theory. So it wasn't until the early 20th century actually that the concept of the neuron was sort of firmly established. So the idea that the nervous system is made up of many individual cells that are not that have a gap between them, so what we call a synapse today. So there were the competing theory through the 19th and early 20th century was the reticular theory, and this was a theory according to which the whole nervous system was one sort of continuous structure, that there was this kind of net. So the word reticular comes from a Latin word meaning net, and so there was this like network structure of nerves that ran through the whole body in one sort of continuous net, rather than being made up of cells. And so the point here to refer to this account, or the fact that the cellular structure of the nervous system wasn't established at this time, is that the sort of reductionist approach to physiological systems only works if you can identify parts that you can study, right? So you can only like break down a system into its parts if you actually can identify parts in the first place. And so if you consider the nervous system to be one continuous net, then you can't really do this reductionist approach of like, what does this part do? And so, so because of this, the the study of the nervous system was sort of resistant to the like typical reductionist sort of mechanicist mode of explanation for a long time. Okay, so I think we can go on to the next passage. If someone could read from Herein Resides.
I can read again. Herein resides the difference between fields of application and validity of the model method of the classical method of experimentation, taking its departure from an hypothesis of a functional. Experimentation is analytical and proceeds by discriminating and determining conditions by varying all other factors being supposed unhinged. The model method allows the comparison of entities which resist analysis. Now in biology, analysis is less a partition than a liberation of entities of a smaller scale than the initial. In this science, the use of models can legitimately pass as being more natural than elsewhere. Before the era of cybernetics, one could believe in the inadequacy of mechanical models of biological systems, which are characterized by their completeness and internal auto-regulation. Today, this opposition seems to have overcome, and L. von Bertalanffy can maintain, on the contrary, that the model method can be applied to the study of organisms because they present the general properties of a system. It is known that Bertalanffy introduced into his general theory of systems the distinction in the last century by comparable anatomists between analogues and homologues, that is to say, between apparent similarities and properly analogous correspondences in the mathematical sense of the term. According to this vocabulary, it is on homologues that rests the elaboration of conceptual models and the possibility of transference of structurally similar laws outside the initial verification. By this approach, we can perhaps observe how the construction of electrical, physicochemical models in neurophysiology constitutes an intermediary at once historical and logical between the mechanical model, reproducer of pattern rather than a simple simulator of effects, and the model of a mathematical or logical type. The spirit of mathematical physics, itself progressively aided by a new mathematical knowledge, that of structures, has found an accessible path into biology, thanks to Maxwell's work in the field of electromagnetism. In modern mathematics, to construct a model is to translate one theory into the language of another, to set up a correspondence between their terms while retaining structural relationships. This implies the isomorphism of theories. In mathematical physics, as it has become following the work of Joseph Fourier, the mathematical theories are taken as an object of study from which analogies arise in experimental fields which are a priori unconnected. These analogies prove the polyvalidity theories in relation to physical. To reconsider the examples which struck Fourier, the propagation of heat, the movement of waves, and the vibration of elastic laminae are intelligible by means of mathematically identical equations. But in mathematical physics, the construction of a model in one field of physics in order to understand phenomena of a different field does not in any way confer a privileged character on the field chosen as a reference of intelligence. The choice of phenomena for analogical reference depends only on one of the two following elements. Either the knowledge of these phenomena has already reached the stage of being, or these phenomena lend themselves particularly easily to experimental investigation. In neither case does the concrete realization of the validity of a literal representation of which the model aims to explain. Maxwell used to say that the physical analysis serves, starting with a partial similar to illustrate one science by means of another. Illustration is not representation. Now, in biology, it seems more difficult than physics to resist the for a representational value. It is perhaps not only the scientific vulgarizer who has a tendency to forget that a model is nothing more than its function. This function consists in lending its type of mechanism to a different object without imposing itself as axiomatic. But has it not sometimes happened that the analogical models of the biologist have benefited from an unconscious validation, having as its effect the reduction to its analogy, mechanical, physical, or chemical? Despite their great degree of mathematical complexity, it does not appear that cybernetic models are always safe from this accident. The magical aspect of simulation is strongly resistant to the exorcism of science. Yeah, I thought this was a really, I found this argument very clarifying and convincing, that in the case of, for instance, the examples that he gives, heat propagation, wave motion, and elastic vibration, I guess, even though the same differential equations can be used to describe propagation of heat and of waves. You wouldn't say that the waves are heat because of the fact that the same equations can be used for both. One really reduces to the other. And part of his argument seems to be that one of the reasons that a reductive approach, or representational, as he's putting it here, is more attractive in biology is because of the complexity and the opacity of the system being modeled. So when you have a very clear model and a very opaque system, it's tempting to sort of the only option that you have into which you have a clear insight is the model. And so it's tempting to just see the system as somehow reducing to or really being represented by. Whereas for the example of heat propagation and wave phenomena, you can use one if it's experimentally easier. The theory is better developed with respect to one theoretical as opposed to the other. You can use the easier, better developed object to explain the second one, because the second one will become illuminated thereby. You don't really risk reducing the target system to model in the same way.
Yeah, I think there's also a sort of sociological factor involved in this, greater tendency towards reduction or towards a reductionist reading of modeling in biology, because of the fact that physics or chemistry or whatever is understood as being like a hard science or harder science compared to the sort of messiness of biology. So like if you can produce a physical model of some biological phenomenon, the physical model is taken as more like it's as harder or better or more scientific or whatever compared to the messy biological reality. And so yeah, there's this temptation to say, look, we've reduced this complicated and obscure biological stuff to this much clearer and simpler and more rigorous physical set of mathematical equations or whatever it is. Therefore, we've like, this is like the model for how, or the paradigm for how we should understand biology in general is like getting rid of the obscure, messy biological stuff and reducing it to this clear and simple physical systems. And again, like Canguilhem is not saying, of course, that producing a physical theory that explains a biological phenomenon is bad or that you shouldn't do it or whatever. It's just this sort of, he wants to sort of resist what he's calling here this sort of magical aspect of simulation. So the fact that you can produce a physical model of a biological phenomenon doesn't sort of eliminate the reality of the biological phenomenon you're trying to understand. Like you've grasped one aspect of it and it might be a very important aspect of it, but of course, there, in general, are many other aspects of that biological phenomenon that are not grasped by that physical model. And maybe I'll explain a little bit the reference to Fourier here, because this is often taken as like sort of the paradigm case of mathematical physics in the 19th century. So Auguste Comte, for example, the sort of famous proponent of positivism, he took Fourier's work to be like, this is the model for what science should be doing in general. Like, yeah, everything from physics to biology to sociology, etc., should all be doing what Fourier did. And so this what he looked at was the propagation of heat. So like if you have, say, a metal bar where you heat one end of the bar, you'll have a difference of temperature, of course, between the end that's in the fire or wherever, and then the other end in the ambient air. But then the heat, of course, propagates down the bar, and you'll get like a sort of gradient of heat from the hot end in the fire towards the cool end in the air. And he kind of just asserts without really giving a full proof of it, but he claims that this that you can sort of reproduce the pattern of the gradient of heat in this type of setup. You can this has a similar sort of mathematical structure as the way that you can take any periodic function and decompose it into a sum, possibly infinite sum of sine waves. So he just sort of asserts this fact about periodic functions without proof. It turns out to be true, which is pretty remarkable. And this is like basically anything that involves digital audio in any form relies on this fact. Like there's like the Fourier transform is like a well-known signal processing tool that like you take a complicated sound wave like a human voice or whatever it is, and you sort of decompose it into these simple sine waves, and then that are sort of added or subtracted from each other, and then you can reproduce the sound on the other end of the whether it's like a stored recording or setting it across a signal in real time, etc. Anyway, you can reproduce the sound in a a comprehensible form or a form that resembles the original sound by sort of reconstructing out of these component sine waves. And it actually just sort of incidentally turns out that there are part of our own like biological hearing apparatus works in a similar way, that the sort of hairs in our ear that respond to sound waves are have like a sort of peak sensitivity range that like in terms of frequency. So different segments respond to different ranges of frequency, and then based on like which of these segments are activated by the incoming sound, it kind of like decomposes the sound coming in into these like component simpler sounds. So like your capacity to recognize, say, like a trumpet versus a violin is dependent on the fact that the pattern distribution of energy across different frequency ranges is different in these two instruments, and so you recognize that based on like the fact that different portions of those receptive cells in your ear are going to be responding in depending on what the sound is. So all this is just to say that this is a huge like discovery that Fourier made, and has applications like all over anything that has to do with like signals, time series, audio, etc. Like his work is fundamental to that. But one of the sort of key elements that that Auguste Comte insisted on in relation to his work is that Fourier didn't give any kind of mechanical or like even really any physical model for what heat was. He just gave a mathematical description of how heat is propagated, and he sort of deliberately abstained from explaining what heat is, what is the nature of heat. And Comte took this to be like the sort of responsible scientific approach. This is like sort of the key idea of positivism, is that we can't know what the essence of anything is, but we can study its behavior and create these mathematical laws for how they behave. Of course, this is something that has been controversial in the history of science, and I think most physicists would say that we do know what heat is now. We don't have to sort of only look at how heat is propagated. We can grasp what heat is. So this was sort of like one, I guess, way of understanding what science does, is that all we can do is like observe different entities, how they behave in certain circumstances, some of which we set up ourselves in the experiments, and then create mathematical laws that sort of reproduce that behavior. But this model, this sort of idea of how science works is much more appealing, I think, to like physicists who are studying these extremely simple systems where you have like for example, in celestial mechanics, you're essentially just treating point masses related to each other only by gravity, in a vacuum. So everything is extremely simplified. You have like one force and a bunch of dots related to each other by means of this force. And so in this context, it does seem appealing to say that all we're doing is just sort of predicting where these dots will be after a certain amount of time. But when you're talking about living organisms, they're so much more complicated than this. It starts to become less, I guess, plausible that all you're doing is sort of predicting what the rabbit will do when it sees a fox or whatever. I don't know, whatever sort of biological scenario you're setting up. But there's so much going on within the organism, and its relationships with its environment are so complicated. The organism can be in so many different states, et cetera, et cetera. It just, this sort of predictive positivist model of science is much less plausible in the case of living organisms. And that's sort of, I think, motivates biologists sometimes to want to it sort of leads them to grasp at this sort of reductionist approach, because the astronomer might not feel that impulse towards reductionism because what they're studying is already so simple and so I guess straightforward to grasp that they don't feel a need to sort of found it in something more fundamental or simpler or whatever. So they can just say, all I'm doing is predicting where these planets will be 1,000 years from now. Whereas the biologist is studying something so complicated and obscure that they feel like they need something firm to sort of found it on. Otherwise, they'll just be like, swimming in this like murky soup of biological mess.
I actually I had wanted to say this in the last section, but it also sort of ties in here. One of the really interesting things about Cajal and Golgi is, so while Cajal's theory of neuronal transduction is like foundational and still correct, he relied on the Golgi stain to formulate this model. And one of the properties of the Golgi stain is it only stains neurons because of the way the tissue's fixed and processed. So in a way, because of the method relied on, it also slowed down or delayed a fuller understanding that other cells in the tissue are also involved in neuronal like glial cells. So I don't know. I've always thought that was really interesting, that if Golgi had come up with a different method for processing the tissue, the entire model may have been different 150 years ago. So just kind of points to the nature of how opaque these systems are and how much we rely on the tools for investigating to build the models. So
Yeah, that's a good point. Sorry, I put the wrong link in the chat here. So I put the link in the chat to Ramon y Cajal and Golgi. So these are two rival early 20th century neurologists. They were jointly awarded the Nobel Prize in 1906, but they were sort of like scientific rivals of each other. Golgi is most famous for this method, the Golgi stain, which essentially, I think it involves silver, if I remember correctly. But the key value of this stain is that it sort of dyes the neuron, a complete neuron, but only a small number of the neurons. So like I think it's about 10%. Like you can inject it into like a slice of brain tissue, for example. But I think it's something like 10% of the neurons take up the stain, but it disseminates throughout the whole body of the neuron. And so part of what's so complicated about studying neurons, or was at this time, is that they of course are very long and they're all sort of tangled up with each other. So if you just like take a chunk of brain tissue, you're gonna have like millions of different neurons, all sort of like different fibers going everywhere and tangled up, and it's extremely hard to like actually see what is going on. But then if you use this stain, you get like a small number of neurons that are that show up very clearly in your preparation, and you can actually follow where does the axon of this neuron lead to. Like you can follow where is the cell body of the neuron and where does this axon go to. So this was like it's a very sort of technical procedure. It's like it's just a useful way of staining a cell preparation of brain tissue where you can see the cells better. But because of this, it was very important to actually identifying the fact that the nervous system is in fact composed of cells that are separate. Yeah, that's a great image. So it shows what it looks like when you do when you take a tissue sample and use this Golgi stain method. Once you do this, you can actually, using a microscope, identify individual neurons, nerve cells, and find out that the nervous system is not just one continuous net. It's actually composed of these many separate cells. So it's like, on the one hand, it's a purely sort of experimental technique. It's just this kind of stain, a kind of dye that you can use. But on the other hand, because it's so helpful in identifying the individual cells, it sort of had this transformative effect on the understanding of the structure of the nervous system. Oh yes, I wanted to come back to this. I forgot about that. Yeah, so you mentioned the other cells. So so this is the other, maybe the negative side of this technique is, as Organelles had just said, is that it only the stain only gets taken up by neurons, and all the other cells that are involved in the nervous system. So there are these other cells called glia. They were sort of, oh yeah, sorry, yeah, we'll wrap up in a minute. Yeah, thanks, Angus. See you. So all these other cells were taken to be sort of like secondary, and so often you'll see that like the glial cells are sort of involved in the nutrition of the neurons. They're sort of like supportive structures, and it's only quite recently that there's been more evidence emerging that they are involved in the sort of what we think of as like information processing and so on, all the sort of traditional cognitive processes of the nervous system. So it's not just that the neurons do all the thinking and then the glia, make sure that the neurons are fed and so on. They're both involved in these processes in these complicated and not really very well understood ways. Okay, yeah. So we're at about the 2-hour mark now. So we'll have to end here. I think we should be able to finish this one next week. And then after that we'll pick up the next Rouillet book. But yeah, so hopefully everyone can come out next week. Thanks everyone for coming. Thanks for your contributions, and hope to see you